Hey everyone, and welcome to today's Explainer. If you've been following the rapid advancements in artificial intelligence lately, you've probably heard endless debates about whether these models are actually genuinely thinking. Well, today we are going to move right past that hype in a calm, methodical way. Our goal here is to pop open the hood and really understand the mechanics of reliable, verifiable AI. To do that, we're looking at a fascinating framework known as the energetic paradigm, which completely shifts how we architect machine reasoning. Okay, let's dive into this. The whole debate over whether large language models truly reason, it almost always gets bogged down in philosophy. But from an engineering standpoint, the real issue isn't philosophical at all, it's operational. The key question we need to ask is whether the transformation from a complex problem to a final answer can be properly structured, inspected, corrected, and actually verified. When a model faces a really hard task, like diagnosing a medical symptom or writing flawless code, what exactly is happening between your prompt and its final output? And that brings us to the core thesis of the energetic paradigm, or EP for short. EP treats reasoning as a managed flow. Think of your initial prompt as raw pressure. The final answer is the output state. The system's job is to manage this flow, converting all that unresolved pressure and uncertainty into verified intelligence through a series of intermediate states. Because, look, reliable intelligence doesn't just magically happen because a model is really good at stringing together fluent, step-by-step language. It emerges when that intermediate reasoning is actively controlled and verified.
So here is the blueprint for today's explainer. We're going to cover 1. Beyond fluent language. 2. Computational infrastructure. 3. The proxy and routing problems. 4. The verifier control gate. And finally, 5. The dependable architecture.
All right, let's kick things off with Section 1, Beyond Fluent Language. We are moving from mere illusion to governed production.
And this brilliantly illustrates the core issue. It's absolutely crucial to realize that a model's final answer is just the surface layer. On one side here, we have generated reasoning. This is where a model might just stumble into a conclusion through lazy shortcuts or raw memorization, spitting out a massive chain of text that looks totally logical but is actually super vulnerable to hidden errors. It's essentially decorative. But on the other side, we have governed reasoning under the energetic paradigm. In this setup, the reasoning is a structured physical transformation. It's actively inspected, corrected, and verified at every single stage. Because honestly, more text does not guarantee better reasoning, and we absolutely shouldn't trust uncontrolled paths just because they sound convincing.
Moving on to Section 2, Computational Infrastructure. Here, we're treating steps as checkpoints, not just decoration. Now, what's really interesting about this is the massive shift in perspective it requires. Those intermediate steps, the step-by-step words the model produces, they aren't just neat little explanations written for your benefit. They are the actual physical computational workspace the model needs to solve hard tasks. Under EP, these reasoning steps are viewed as controlled energy channels. By forcing the model to take intermediate steps, we effectively slow down the entire conversion from prompt to answer. And that slowdown is huge because it allows the system to localize exactly where an error happens, redirect the pressure of your query, and constrain the final output using visible structure. So by slowing things down, EP turns these steps into specific, rigorous inspection checkpoints. The system can actually stop and ask, okay, which premise is active right now? Which specific operation was just performed? What exact subresult did it produce? Are our initial constraints still being satisfied? And if something goes off the rails, where exactly did the error enter the chat? Under this paradigm, a step is literally only valuable if it performs a valid transformation under these strict constraints. But of course, here is where a major problem pops up: decoding. When a model generates text, it usually relies on something called greedy decoding, which just means it selects the most probable next word. It's a routing problem. It's kind of like when you're working through a complex arithmetic problem, and you just grab the most tempting, immediate number instead of thinking 2 steps ahead. The protected flow in greedy decoding is speed and simplicity. But the sacrificed flow? That's exploration, path quality, and error recovery. The wild thing is, the correct reasoning path might literally exist inside the model's head, but greedy decoding simply fails to route the computation through it. Which brings us perfectly to Section 3, the proxy and routing problems. We'll see exactly why prompting and basic imitation just aren't going to cut it anymore. You might be wondering, well, can't we just train the model on human examples or use better prompts? The problem is that supervised training often just teaches the model to blindly imitate the inconsistent style of human reasoning. It's optimizing for appearance, not verified correctness. We call this the proxy problem. And what about prompting? Telling a model to think step by step is a fantastic trigger for sure. It activates a capability. But, and this is key, prompting leaves all the authority inside the generator. EP control is fundamentally different. It acts as an independent gatekeeper that actually determines whether that reasoning path is allowed to pass. Think of this whole thing like a really strict factory assembly line. The EP control layer achieves this verified reasoning through a rigorous pipeline of physical gates. First up, task framing defines the exact transformation required. Second, constraint extraction identifies the rules that absolutely must remain true throughout the process. Third, path monitoring tracks the actual progress. Fourth, failure detection spots invalid reasoning early before it ruins the final output. And fifth, final validation confirms the absolute correctness of the end result. It is a strictly governed, locks-down process.
All right, Section 4, the verifier as a control gate. We are shifting from pure imitation to controlled selection. This introduces the absolute hero of this whole architecture, the verifier. If mere imitation hits a ceiling, which it does, we have to shift to a verifier-driven regime. The core idea here is that a reasoning system is entirely controlled by the gate deciding which outputs actually count. If you have a weak verifier, your model is just going to confidently amplify its own errors during self-improvement. But with a strong verifier, that enables the controlled reproduction of correct reasoning. The generator throws out possibilities, but the verifier is the ultimate judge of what survives. And that creates this incredibly powerful self-improvement loop. The model will generate a diverse set of candidate paths. Then, the verifier evaluates those outcomes against our strict constraints. Any invalid paths are ruthlessly rejected, the valid paths are retained, and finally, those successful paths are used to reinforce success, literally shifting the model's future probability distribution toward verified reasoning. But listen, even with an amazing verifier, relying on just a single generation path can be super brittle. A single direct answer is fast, sure, but it carries a massive risk of the model taking shortcuts. That's exactly why EP relies heavily on self-consistency. This is basically a multi-path stability test. The system samples multiple different reasoning routes to see if they all converge on the exact same answer, creating a distributed, reliable field of evidence. It's the difference between asking one random person for directions and hoping for the best versus asking 5 different people and only going the way they all agree on. Let's move to Section 5 and see how this all builds into the dependable reasoning architecture. This is all about handling external inputs and open-ended verification. So far, we've talked a lot about internal reasoning, but what happens when the model just flat out lacks the necessary facts? That's where retrieval comes in, acting as an external evidence channel entering the system from the outside. But warning, it has to be strictly governed, or you'll just overwhelm the reasoning path with garbage data. EPO governs this by asking tough questions. What specific uncertainty must be reduced? Which external source is actually authoritative? How exactly will this new evidence constrain our reasoning? And most importantly, how is the correct use of that evidence verified? It turns a random web search into a highly controlled evidence channel. Now, verifying a math problem or a block of code is relatively straightforward. There's usually a clear right or wrong answer. But what about open-ended domains, things like business strategy, law, or medicine? Well, for those, EP uses an open-ended composite verification structure. It checks constraints, verifies causal mechanisms, assesses evidence reliability, evaluates intervention stability, and even monitors computational cost. The goal here isn't to magically eliminate all uncertainty, that's impossible, but to make the model's judgment traceable, constrained, and easily corrigible. So the crucial point is this powerful summary. The final distinction is not between models that reason and models that do not. The deeper distinction is between reasoning that is merely generated and reasoning that is rigorously governed. Uncontrolled reasoning just wastes computational resources, propagates hidden errors, and ultimately fails us when the stakes are at their highest. We really have to stop viewing AI reasoning as a casual conversation and start viewing it as a meticulous production system. Look, AI can generate language that mimics deep thought all day long, but the energetic paradigm proves that true, reliable intelligence isn't magic. It requires turning raw uncertainty into candidate paths, verifying them, correcting them, and governing the entire transformation. So the next time an AI hands you a brilliant step-by-step answer, don't just be blindly impressed by the text. Ask yourself, was that intelligence merely generated, or was it rigorously governed? Thanks for joining me on this explainer.
and keep questioning the architecture behind the answers.